Hello, thank you for watching this video. Today we will talk about chapter 4, frame relay. Frame relay is divided in two parts. We have part 1 and part 2. This is part 1 of CCNA exam semester 4, Connecting Networks, by me, Astrid Krasniqi. Okay, in this chapter we will talk about introduction to frame relay, or introducing frame relay, advantages of frame relay, virtual circuits, multiple VCs, the frame relay encapsulation process. Then we'll talk about frame relay header, star topology and hub and spoke topology, full mesh topology, frame relay addressing mapping, local management interface LMI, frame relay configuration tasks, and then I'll do a demonstration about configuring basic frame relay with the static maps. Okay, introducing frame relay. Frame relay is a high-performance wide area network protocol that operates at the physical and data link layer of the OSI reference model. Layer 2 protocol of the wide area network. Do you remember any other layer 2 wide area network protocols apart from frame relay? Well, if you watch the previous videos, we talked already about point-to-point protocol. That's layer 2 wide area network. And what else do we have? HDLC, Cisco proprietary, the wide area network, layer 2. So they don't work in layer 3, this is just layer 2. Eric Skase, an engineer at Sprint International, invented frame relay as a simple version of the called X25 protocol to use across integrated service digital network ISDN interfaces. Now X25 is being replaced by frame relay because X25 was using these long headers for reliability, which frame relay doesn't need them anymore. Frame relay connections are created by configuring CPE routers or customer premises equipment routers or other devices to communicate with the service provider frame relay switch. So you configure frame relay by configuring your routers to connect to the ISP's switch, frame relay switch. Advantages for frame relay. Frame relay reduces network costs by using less equipment, less complexity, and easier implementation. Let's have a look at this network. For example, in this network we have, say that's the hub, and these are like the spokes. This is a point-to-point, for example, leased line connection. Now, all these points, they will be quite expensive to buy. Like you need to purchase the IP addresses, they're going to need their own subnet, and for the lease line, the bandwidth, and so on. So with the frame relay, what we can do is we can connect to the ISP, which is the cloud, and then from ISP we can create all these virtual links. So for example, the hub now has only one link towards other destinations, so it doesn't need to pay extra IP addresses, extra interface cards, and so on. As long as it's got connection to the cloud, that's it. It can connect. It can have a virtual link to every other spoke. Plus, you can have links from spoke to spoke through the virtual links. Now, frame relay specify how data moves between the DCE, data communication equipment, and DTE over local loops. So here's the ISP's frame relay switch, and the frame relay specifies how data moves between your router, CPE, and the frame relay switch. Frame relay does not specify how frames moves between DCE across the wide area network. So it doesn't specify how it moves between the two spokes, for example. A frame relay 1 is a mesh of switches interconnected by trunk links. So as you can see, these inside the cloud, they will be connected switches or frame relay switches. This is from ISP. They will be on the full mesh in there. Now, how the data travels from one area to another area in the cloud is not our concern. We are more worried, is the data going to get there, rather than the path that it's going to take. We in the cloud, we're not concerned. Virtual circuits. The connection through a frame relay network between two DTEs is called a virtual circuit. So if you connect two spokes or two branches together, then that connection is called a virtual circuit. The circuits are virtual because there is no direct electrical connection from end to end. So you connect in one branch to the ISP and then goes through the cloud, which we don't know what happens in the cloud, and goes to the destination to the other branch. There are two ways to establish the virtual circuits. First, it's switched virtual circuits are established dynamically by sending signaling messages to the network. So when you need to establish this switch circuits, the source will call the destination. It will be like established only when there's a need to transfer some data. Do you remember the other virtual circuits? Okay, here we go. Permanent virtual circuit are pre-configured by the carrier, and after they are set up, only operate at data transfer or idle modes. So they either transfer in the data or they are just sitting there idle, but it's always on the connection. So you don't need to dial any number or anything, it's always there. So virtual circuits are identified by data link connection identifier, or DLCs. Frame relay DLCs have local significance, which means that the value themselves are not unique in the frame relay 1 DLCs. So this, imagine the two branch offices that we're going to connect together. One branch connecting to the other branch. Now that connection is called a virtual connection, virtual circuit, because there's not a direct connection between those two, but they will behave, the data that it will transfer, the configuration, it will be like point to point. And those virtual circuits are identified by something called DLCs. Now these DLCs are local significant only, so between your router and the ISP's router, or ISP is going to give you the DLC number. Now that DLC is not unique. Another ISP can give the same DLC to another router. For example, with the virtual circuits, it's the best way I describe this through, like, if you are in the airport. Now in the airport you have a ticket. In that ticket it will say to you what gate you need to go. Now you didn't choose that gate, but airport told you. It's a gate 15, for example, and gate 15 will take you to New York. So if you want to go, imagine yourself, you are the data. If you want to go from here, from London to New York, you have to take gate 15. Now in the New York airport, gate 15 could mean something else. The gate 15 could take them to Paris. So it doesn't mean that it's exactly they will have the same gate or same DLCs from the source to the destination. So DLC has no significance beyond a single link. DLC 0 to 15 and 1008 to 1023 are reserved for special purposes. So we have 16 to 1007, sorry. Okay. Now, multiple virtual circuits. A frame relay is statistically multiplexed, meaning that it transmits only one frame at a time. But that many logical connections can coexist on a single physical line. The frame relay access device, FRAD, or router connected to the frame relay network might have multiple virtual circuits connecting it to various endpoints. For example, you have a connection to your ISP. In there we can create these virtual circuits that we can have one virtual circuit going to Paris, one virtual circuit going to New York, but we have only one connection to our ISP. Our ISP can create the virtual circuits for us. Now, frame relay access device, I just put it out there because you might see it in the exam or something, and this acronym, and it might scare you. So it just means a router, really, your router, your customer premises equipment, CPE. Multiple virtual circuits on a single physical line are distinguished because each virtual circuit has its own DLC. Yeah, that's true. Virtual circuit. So imagine that there's from London we're going to New York, another one virtual circuit, and another virtual circuit is going to Paris. Now they're gonna be distinguished with these DLCs. For example, DLC 15 goes to New York, DLC 25 goes to Paris. It's like gates, you remember, in the airport? One gate takes you to New York, the other one gate takes you to Paris. So multiple virtual circuits, for example, we looked at here, this one, for example, is London, we're saying. If we take this DLC is going to take us to New York. Imagine this is the New York router. if we go take this delta, it will take us to Paris. Any other one, I don't know, somewhere else, Bonn or Berlin or something. Okay, so in this router we will create configure our deltas. Delta 1 or 2, for example, will go the blue way. Delta 1 or 3 will go through the green link, and 104 will go through the black link. Now, if we want to send some data to New York, we have to encapsulate the data with the appropriate delta. That's the router will say, okay, I have some data, I want to send it to New York, I'll encapsulate it with the delta 1 or 2. When I send it to this packet to the ISP switch is going to look and says, okay, this is delta 1 or 2, needs to go to New York, and so on. So the frame relay encapsulation, frame relay accepts the packets from the network layer, protocols such as IP, and then it wraps, it encapsulates the packet in which the address field contains a delta. It will have the delta on the address, and flag fields are added to indicate the beginning and the end of the frame. So as you can see here, we have a flag field. Here it has the start of the frame and another flag field, the end of the frame. We have the data, and then we have the address. That's the address. It's called the whole delta. It's inside the address. We'll see the header. That's the header of the frame relay. So frame relay header, we have first delta, data link connection identifier, delta. Then we have a CR, EA, forward explicit congestion notification, backward explicit congestion notification, and discard eligible. Okay, we go one by one. Delta. Delta is 10-bit in the essence of the frame relay header. This value represents a virtual connection between the DT's devices on the switch. Each virtual circuit or virtual connection that is multiplexed on the physical channel is represented by unique delta. The delta value have again local significance only, which means they are unique only to the physical channel on which they reside. So here we have a delta, is a 10-bit, represents a virtual connection to another DTE device, and it will have each virtual circuit will have its own delta, and it will be locally significant. So imagine you have for example, 4 tickets going to different destination. So first ticket will have gate 15 going to New York, gate 25 going to Paris, gate 35 going to Berlin, and so on. Now, when you go and give these tickets to the airport, then they just have a significant on that airport. So it's locally significant. What the airport does, or what the frame relay switch does, is not our concern. We just give the ticket with the encapsulated delta, and then the frame relay switch will take it to the destination. Then we have a CR. The CR bit is not currently defined, so you don't have to remember anything in there. EA, extended address. If the value EA field is 1, the current byte is determined to be the last delta octet. It just says which byte is the last one. If it's 0, there's another byte coming. Forward explicit congestion. A bit is set by a frame relay network to inform the DTE receiving the frame that congestion was experienced in a path from source to destination. So the frame relay ISP or something will tell the destination, will say, okay, well, here's the packet, or here's the data that we sent, the frame. Now you got it, but there was a congestion, so there might be errors on there. And then we have a backward explicit congestion notification, and at this time it's sending it to it's telling the sender that there was a congestion. And then we have a discard eligible. Now discard tag traffic that can be dropped to ensure delivery of higher priority traffic. So some of your data you will be not as important as some other data. For example, if you have a data like a web browsing, it's not as important as a video or voice data. For example, if voice data gets dropped, then the communication will be a problem. But if for example, web browsing data gets dropped, that means it's not a big problem. For user, maybe we'll get the web page 1 or 2 seconds later, but it's not going to notice the difference. If a user gets the voice 1 or 2 seconds later, or might not get it at all, then there will be a problem. So again, the frame relay header, we have a DLSI, a link connection identifier, CR, EA, forward explicit congestion notification, backward explicit congestion notification, and then discard eligible. Star topology, or another word, hub and spoke. So we have a hub, and all the other branches are considered to be the spokes. So that's a star topology. With the star topology, the biggest problem that could happen is if this hub fails. If this router fails, then all the spokes, they will be alone. So on the star topology, we have the simplest one topology is a star. Connection to each of the 5 remote sites act as the spokes. In a star topology, the location of the hub is usually chosen by the lowest least line costs. And when implementing a star topology with the frame relay, each remote site has an access link to the frame relay cloud with a single virtual circuit. Full mesh topology, on the other hand, it's every router will have access to every other router. Now this is the best if you can afford it, because it doesn't matter if one of the branches fails, every other branch will have a connection to every other branch still. It will still be working. Now it's money, because it will have a virtual circuit, so every time you bring another router, you have to add so many more virtual circuits. A full mesh topology suits a situation in which the services to be accessed are geographically dispersed and highly reliable access to them is required. A full mesh topology connects every site to every other site. And the formula, it's n times, on the bracket, n minus 1. Example, on this we had 5 routers. So 5 routers times 5 minus 1 is 4. So 5 times 4 equals 20. For this topology that we had, we will need 20 connections. Okay, now if we had, for example, 9 routers or 9 branches that we want to connect, what do you think? How many virtual circuits do we need if we want to connect them full meshed? So if we had 9, then this n will become 9 times 9 minus 1, so it's 8. So 9 times 8, so we will need 72 virtual circuits. Another topology that is we're not going to show it here, is called partial mesh. For example, if you want something like this, but you don't really, maybe it wants some branches you don't want to connect to every other branch, then that will be considered a partial mesh. Example, this router here, or this branch office here, maybe doesn't need another connection to this branch office here. So if we cut this connection, just because we did that, we cut that connection, now it's called partial mesh. Okay, frame relay address mapping. Before a Cisco router is able to transmit data over frame relay, it needs to know which local DLSI map to the layer 3 address of the remote destination. So it needs to know what DLSI to use, what layer 2 data to add, or header to add on top of it. So it's going to do that through dynamic mapping or static mapping. Dynamic mapping, address mapping relies on inverse ARP to resolve a next hop network protocol address to local DLSI value. So it will use inverse ARP to resolve that layer 2 to layer 3 mapping. Remember from ARP, address resolution protocol, it was resolving layer 3 addresses to layer 2. For example, if you go and ping, say ping 192.168.1.1, now the router maybe doesn't have a MAC address for that, so it will send an ARP request. It will say who's got that address. It will broadcast that, and then the device that has that address will reply. Will say, okay, yeah, it's me. Here's my MAC address. Well, similar idea is happening with inverse ARP, but inverse ARP is resolving layer 2 to layer 3. So now we need we have a layer 2, but we want to resolve to layer 3. The frame relay router sends out inverse ARP request on its PVC, permanent virtual circuit, to discover the protocol addresses of the remote device connected to the frame relay network. The router uses the response to populate an address to dulce mapping table on the frame relay router or access server. Static mapping, which I think is better, I prefer more anyway. Inverse ARP, we really just always pretty much disable it and we go with static mapping. We want to be in control. The user can choose to override dynamic inverse ARP mapping by supplying a manual static mapping for the next hop protocol addresses to local dulce. For example, the command will be, this command is not supported in packet tracer, so don't go and try because it won't work. So you go to the interface and say no frame relay inverse ARP. Now this command is not going to be available if you don't have encapsulation frame relay. So after you do encapsulation frame relay, you say no frame relay inverse ARP. And then you have to supply a static mapping. So frame relay map IP, then you map in IP. You can map IPX, AppleTalk, you can map different protocols. But this time we map in IP, and this is the destination. Is the IP address of the branch, of the other branch. So 10.1.1.2 in this case. And what is our local dulce? So what ticket or what we're gonna use, what header we're gonna use. So this is our dulce 102, and then broadcast. This will be used for example, for routing. Local management interface, LMI. LMI is a keep alive mechanism that provides a status information about frame relay connection between the router and the frame relay switch. So LMI is what we keep to make sure that the connection between us, the router, and the ISP is on, is live. Not from us to the other branch, to the other side, to the destination, but just to our ISP. So this is layer 1 and layer 2 mechanism to make sure that us, source, sorry, and the root and our router and the ISP, the connection is alive. So every 10 seconds or so, the end device, which is our router, will poll the network, either requesting a dump sequence response or channel status information. If the network does not respond with the requested information, the user device might consider the connection to be down. When the network responds with a full status response, it includes the status information about dulce that are allocated to that line. There are 3 types of different LMIs that Cisco supports. Sorry. Okay, the first one is Cisco Original LMI Extension. This is the default as well. So if you don't touch the LMIs, you don't get asked about to do anything with LMIs, this is the default. Then we have ANSI and Q933A. These are the open standard LMI that Cisco does support them as well. Now to you, for example, your router and the ISP's frame relay switch, the LMI type has to match. This one has to match. For example, if the ISP is using ANSI, we can't use Cisco. We have to match the LMI. Configuration task, we have a frame relay cloud there, and we have 2 routers. So we have require tasks and optional tasks separated, frame relay. Now, require task, we have to enable frame relay encapsulation on the interface. So we have to go to the interface and say encapsulation frame relay. Otherwise it won't work. This is the required, you have to do this. And configure dynamic or static address mapping. They need to know what address or what dulce I'm going to map it to, what IP address, where is my destination. Optional task, we can configure the LMI. For example, if the ISP is using different LMI than our default, we have to go and change it. Configure frame relay switched virtual circuit. Configure frame relay traffic shaping if we have to do that. And customize frame relay for your network. For example, router 1, we have interface serial 0/0/0 with IP address 10.1.1/24, so that's the commands. You should be professional at this so far. Change the bandwidth. We have to make sure that we put the correct bandwidth in there. And then the command to enable the frame relay is encapsulation frame relay. Once you do that, all the frame relay commands are available now. And first, what I would do, if I can, because in packet trace I can't, say no frame relay inverse ARP. I want to map statically, rather anything dynamic. So if our ISP says that we're giving us a frame relay or DLC number 102 to go to router 2, we have to type frame relay map IP address. So frame relay map IP, the protocol, then the address of the destination 10112, that must be router 2, and the DLC is 102, the DLC that has been given us by our ISP, and we're going to use broadcast. So protocol, so this IP here, this mapping is a protocol, defines a supported protocol. We have AppleTalk, DECnet, IP, IPX, so on. Then we have a protocol address. So this is defines the network layer address of the destination router interface. I have to stress again, that's the destination, that's where it's going. And then we have a DLC, defines the local DLC used to connect to the remote protocol address. And broadcast, this is optional, allows broadcast and multicast over the virtual circuit. This permits the use of dynamic routing protocol over the virtual circuits. That's pretty much, we always going to need the dynamic routing, so I would always put it on in there. Okay, now I'm going to show you a demonstration on configuring a basic frame relay with a static mapping. Okay, this is a packet tracer activity 3.2.2, configuring basic frame relay with static maps. Okay, I got packet tracer here running, so I'm going to connect to the router 1, for example, first, and then start configuring some frame relay commands. Go to CLI and arrange these so we can see it. Okay, now the commands, I'm going to do them on the notepad. So I'll open the notepad here, and the commands that I'm going to do is first I'm going to go to the interface. So this is for router 1 commands. So interface serial all zeros, encapsulate. Before you do no shutdown, don't do the no shutdown first. So encapsulation frame relay, no shutdown. Now that's it, because the interface is already partially configured on this exercise. So as you can see, this is the interface that we are talking about. It's got description already, description linked to the frame relay network, IP address, it's got IP address, and the interface is shut down. So if I go to that interface, config T, interface serial 0/0/0/0, and I do frame relay, that's most of the commands I start with, and then I can type the rest of the commands. Okay, so encapsulation frame relay, no shutdown. Now I'm just going to copy this, right click, copy, paste. Okay, now the interface is up, so do show run. Just want to check the commands that we have there, encapsulation frame relay. And now I'm going to see do show IP interface brief. Okay, now it says here up serial 0/0/0 10/1/1/1, that's what we're interested with. Status is up. Do you remember the status? This is layer 1 information, so status is up, and protocol layer 2 information is down. So there's a problem between us and the internet service provider. There's a problem. There was 2 required tasks that we had to do. First one was to encapsulation frame relay. Yep, that's done. Do you remember the next task, what we have to do? We had to map, yeah? So we say frame relay map, then the protocol. What we're mapping? We're mapping IP address to the neighbor, which is 10.1.1.2, and the protocol, that's the DLC number 102, and broadcast. That's the frame relay map IP of the neighbor, and we are mapping to this DLC. Now in this exercise we have another DLC. So yeah, frame relay map IP 10113, and now with the 103 and broadcast. So we're just mapping two neighbors. We are mapping Dulce 102 to this neighbor, to this destination, and Dulce 103 to this neighbor or destination. I'm going to highlight all of that, copy, paste it to my router. Done. I can do NEND or do show IP interface brief. Okay, it's going to come up very soon. Let's see. The ISP done, all green there. It's going to come up. Okay, now we're going to do the similar configuration for router 2 and router 3. So router 2, information here, and router 3, information here. We're going to put it. I'm going to copy this stuff from router 1, so I don't have to type it again. Go to router 2 and paste it there. But I'm going to change some of these dulces. So let's see. Frame relay map 10111 in the end. And this must be 201. Let's see the information here. Yep, 201 this is. So we're mapping to router 1 with the Dulce 201, 10111. And with Dulce 203, we're mapping to that IP address. So 203 is going there. I'm going to copy all this to router 2. Go to router 2 there. Enable. Config T, right click, paste there. Okay. Do show IP interface brief. Okay. This interface is still down. It says down there. Let's see. Let's wait a few seconds. Okay, we're gonna go and do the similar configuration for router 3. So paste that stuff that I had in the memory there. Then interface 0000, encapsulation frame relay, no shutdown. Yep, frame relay map 10111. This is going to 301, and 10112. This is going to 302. Okay. There we go, 302, yep. So highlight all this, copy, go to the router 3, and paste all that stuff. So enable, config T, right click, paste. Okay. Do show IP interface brief. And it's still saying up and down. Okay, let me see. Maybe the cloud is not configured. Oh, we can go there. Okay, I just looked at the lab right to the end, and the LMI. The only reason why they're not going up is because the LMI. What the ISP is using, it's ANSI, and what LMI we are using is Cisco. So to verify it, do show interface serial 000, and there we can see the LMI type is Cisco. Now that's the Dulce LMI Dulce 1023. Maybe that's wrong there as well. Let's see. Do show frame PVC. Yeah, we have Dulce 102 and it's active, and Dulce 103 as well, and that status is active as well. PVC status active. Okay, so we're gonna go in there and change the LMI. So interface serial 000, which I'm already in there. I'm just gonna do this on the notepad. So make sure the LMI is correct as well. So here we're saying frame relay LMI type ANSI. Same command is for the other two routers as well. Here and for router 3. Okay, so I'm gonna grab all that stuff again, copy, go to router 1, right click and paste it. So if I do show IP interface brief, now 000, it's up both sides because the cloud was using ANSI. Okay, so I'm gonna copy all that stuff again for router 2. So highlight it, right click, copy, go to router 2, right click, paste. Do show IP interface brief. Brief. Yep, 000 is up as well. Okay, I'm gonna check as well to router 3. Repeat the command. Router 3 has got still down. Oh, maybe because I haven't copied it. So right click, copy that. Right click, paste. Okay, here we go. Do show IP interface brief. Yep, this is up as well. Excellent. So now we can go to router 2 and just see if we can ping the neighbors. We could have done it for many routers. Do ping 10.1.1.1. Yeah, we have a reply, and .3 we have a reply. Excellent. So this is showing you how to configure a frame relay, basic configuration steps, into just configuring frame relay with the static mapping. Remember, we have to enable encapsulation frame relay. These are required tasks, and then we have to configure mapping. Map DLC to layer 2 or to layer 3, DLC to an IP address. Okay, this is what we covered in this video. We looked at the introducing frame relay, advantages of frame relay, why is it important or better for our money to have a frame relay. For example, if we had 4 or 5 branches, we want to connect them together, it's more expensive if we buy point-to-point links. Frame relay, we can just buy one link to the ISP and then purchase a virtual circuit. Virtual circuit is from 2 branches. The connection is virtual because there's no real electrical path. Multiple virtual circuits we can have with one connection to our ISP. We can have a different path, different virtual circuit paths to different destination. The frame relay encapsulation process, we looked at it. The frame relay gets from layer 3 the data, and then it will encapsulate it. It will add its own address as a header. Then in the frame relay header, we looked at different types, what's inside the header. We looked at the star topology, hub and spoke, full mesh topology, and partial mesh as well there. Then we looked at frame relay address mapping, 2 different kind of mappings that we have, static or dynamic. I said static I prefer more, but dynamic is useful as well. So local management interface, then we look, that's a connection, making sure the connection is active between you and the local internet service provider. And then we looked at the frame relay configuration tasks. Then we saw the demonstration configuring basic frame relay with the static maps. Thank you very much. This has been Astrid Krasniqi from helping you to configure and understand a frame relay switching. Bye.